And thank you very much for the invitation. And I'm very happy. So Bangalore is the first city of India I visited. So I'm happy to come back to Bangalore after 14 years. And so today's talk is p-adic L-function over CM field. And this is joint, oh, sorry. Oops. This is joint work with Takashi Hara. Oops. Oh, sorry. How can we come back to? I don't know how to make it larger. Okay, so I prepared usually prefer talk on the board, but the interpolation property of the L function, p-adic L function is so much, very much complicated. So I decided to talk with slides. And afterwards, I prepared, and finally, I had 41 pages. So I'm sure it's too much, and should be very quick. And I don't know, I can finish in time. So anyway, I put the website, the file of my talk already on the website. So during the talk, if you have a laptop, you can download and you can look the file. Okay, so this is the contents of my talk. And first, I review Artin p-adic function over C, and also some basic things on algebraicity of special values. This is necessary for the interpolation property of p-adic function. Then I recall the previous work of p-adic Hecke function due to Katz and defined by Hida-Tilouine. And so final section is our result and a brief explanation of the idea of proof. Okay, so the main reference of the talk is these papers, and Greenberg constructed p-adic Artin L function in these two papers. So basically, our work is generalization, extension of his work to CM situation. And this is our previous paper. So we use some techniques developed in our previous paper. And the talk, the result of this talk is still in preparation. And we are now writing the paper. Okay. So Hecke had L function. So if we have algebraic Hecke character of finite order, then we can define Hecke L function of eta by this kind of Euler product. And this, okay, so this is a definition of the Hecke L function. And the basic things on this Hecke L function is first, this Euler product defining Hecke L function is absolutely convergent on the region, on this region. And this Hecke L function is holomorphic and non-zero on this region because this absolute, this infinite product is convergent. This is the same as what happens for Dirichlet L function. And also, we have functional equation. So first, this lambda things is completed L function. So we multiply gamma factor to the original L function, and this is lambda. Then with this lambda, we have this kind of simple functional equation with epsilon factor. And eta is dual, eta check is dual Hecke character. And then if eta is non-trivial, we know that L function is holomorphically continued to the whole C plane. And if eta is trivial, by definition, this L function coincides with the Dedekind zeta functions, zeta case of number field K. Then I recall Artin function. So somehow Artin function is a generalization of Hecke function of finite order Hecke factor, Hecke character, Hecke character. So we consider, so this already appeared in the yesterday's talk, and we consider continuous representation to Q bar, to GLN of Q bar. So since this Q bar has discrete topology, we have finite image, and this is Artin representation. And Artin function for this law is also defined by Euler product, but then this is Galois representation. So we consider characteristic polynomial of Frobenius of lambda are all prime ideals of OK. And if law is ramified at lambda, we consider inertia invariant part. So we can define this way. Artin L function. So again, it is easy to see that this this Euler product is absolutely convergent on the same region, and also by the same reason, this L function is holomorphic and non-zero on this region. And I made a mistake. So this is law, and I meant law and law dual. Yeah, I just copied. Sorry. So if we consider same kind of completed L function for law, we can define lambda, and again we have a functional equation with contragradient representation of law. And if law is Galois representation of dimension 1 by the global class field theory, this Galois representation corresponds to your Hecke character of finite order. So in this sense, Artin L function is regarded as a generalization of Hecke function, which I talked previously. And this also explained in yesterday's talk. So if we have two Artin representation, and if we consider direct sum two representation, L function for this is product of two L function for law and L function for law prime. This is easy to see by definition. Okay, so since every Artin representation is direct sum of irreducible representation, then we just consider irreducible representation. And so for each irreducible Artin representation, we have classical conjecture like this. So if law is non-trivial irreducible Artin representation, then we conjecture that Artin L function is holomorphically continued to the whole C plane. And this is not completely solved yet, but very classical result is as follows. And if law is Artin representation of the alpha Galois group, then Artin L function, we know or at least that Artin L-function of law is meromorphically continued to the whole C plane. So this we can prove by Brauer's induction theorem. And this proof, maybe this is known to the audience, but this is related to the construction of p-adic L-function part also. So I briefly recall what we do for the proof. So for the brief sketch of the proof, we remember that if G is a group and if H is a finite index subgroup of G, and then we consider and then for any representation, linear representation of this subgroup, we can define induced representation this way. And this induced representation also interpreted like this. So this is just defined by tensor product of group ring CG. This was the representation space of this induced representation. So then what is Brauer's induction theorem? So we consider any linear representation of a finite group G. Then there exists a finite number of subgroups from H1 to HR of G, and degree 1 character phi I for every I, and R integer A1 to AR, and then we have law is sum like this, and so AR times induced representation of phi I from HI to G. So this is Brauer's induction theorem. So I just give basic caution, and so if AI is positive, this sum simply means the direct sum of this induced representation with multiplicity AI, but AI can't be can be negative. I see. Okay. And so we consider this only as virtual representation. So when I is negative, we take a dual representation and sum of dual. So this is important in the later part of the talk. Okay, so what we do in our Gara representation, Artin representation, is that we take K-law to be the finite extension of base field K, which correspond to the kernel of K. And so Artin representation of GK factors like this. And by Brauer's induction theorem, there exists finite number of intermediate fields of this finite extension, K1 to KR, and Hecke character of finite order of each Ki. And we denote, if we put this symbol on Hecke character, this means that Gara character corresponds to this Hecke character by the global cross field theory. And then Brauer's induction theorem says that we have this data, and rho can be represented, expressed like this as virtual sum of induced representation. So, L-function and this first induced Galois representation of this is the same as this Hecke function, and this law is expressed as virtual sum, like in the previous page. LOS is expressed as the product like this. So even if phi I is non-trivial, AI can be negative. So we never know that LOS is holomorphic, but this way, at least we know that this function is meromorphic. That's what we do for the proof. And okay, so that's only thing I talk about this classical conjecture on the holomorphy of LOS. And of course, nowadays, there are a lot of results using modularity of p-adic modular forms. And for the example of classical conjecture, but I don't go into this topic this time. Okay, so in the next section, I talk about the algebraicity of special values, because if you want to consider p-adic function, usually what we define, the way we define the p-adic function is through the interpolation property, and we need the algebraicity of the L function over C. So first, I consider the case of non-trivial algebraic character of finite order. And first, I consider the case of where K is totally real. And then by considering yes, complex conjugate in Galois group, we have two cases. So if we consider positive special values as positive integers, we have algebraicity like this. So if n is maybe well, isn't correct?
Because the for real quadratic, for example, for simplicity, the finite order character, which has at one place signature character, at the other place the trivial, then it won't have any algebra critical point.
Okay, so maybe I should modify somehow, but I don't know how to do it right now. All positive or all negative. Yeah, just we understand this way. Yeah. So if you write this way, all positive or negative. Yeah. Then anyway, if positive integer like this satisfies this parity condition, this is so-called, this is satisfying so-called critical condition, and special value can be algebraic after divided by period. And in this case, period is just power of pi, and we have this kind of algebraicity. And for negative integers, the good integers is this negative parity one. And if n satisfies this parity condition, then this point is critical. But in for negative integers, period is just trivial. So special values itself are algebraic. That's what happens. So questions?
Yeah. So you've written in one case n greater than 1 and in one case n greater than 0. But by the functional equation, or does it not work so simply? These would be symmetric to each other. And so algebraicity on one side would imply the other?
Yeah.
Yeah, so the gamma factors would factor in there. Maybe they would be pi.
Yeah.
Yeah.
That's what happens here. So like it's similar to the case of Riemann zeta function and the Dirichlet function.
Yeah.
Anyway, I'm sorry for that. It was not completely precise, but anyway, you have algebraicity like this. Okay, we go on. So as I said, these integers satisfying good parity conditions is called critical. And the problem is if K is not totally real, we have no critical points. So if we want to define p-adic function, in cyclotomic p-adic function, we cannot do it in a classical way. So that's a problem. But somehow we can consider other kind of p-adic function. We don't consider cyclotomic direction, but we consider other. There are a lot of points in weight space of this CM field. So we don't consider cyclotomic twist, but we consider other twists by Hecke character of various weight. So that's what we do for CM field. Okay, so now we consider exploring what we do in CM case. We consider a CM field of degree 2D, and then we have so cyclotomic case. I didn't talk about p-adic function in totally case, but that case it is one variable and cyclotomic, and then in CM case we will have d plus one variable. We will talk about it later. And okay, so before we do that, we consider what happens with CM field K. We consider CM field of degree 2D, and by this symbol, we consider the set of embeddings of K to C, and inside IK, we can choose a subset called CM type, so which is a subset like this. And basically, we just choose one CM type and we fix it. And then let us consider an algebraic character. In this case, not necessarily of finite order. And then, so finite order case correspond to type 0, 0. But in general, we can consider type. So it is somehow like weight of modular Hom, and there exists so we consider multi-index in this set, and if we consider algebraic Hecke character, usually for eta we have this pair, and the restriction to infinity part coincides with this kind of algebraic character. So this is the type associated to this Hecke character. And we always use board index, board notation, weight like this, and each component at sigma is denoted by this kind of small m sigma and n sigma. Okay, so again, there is a so-called critical condition for algebraic Hecke character. So algebraic Hecke character eta is called critical if Mn satisfies either this inequality or inequality like this. So there m sigma satisfies is smaller than -1, and the second case n sigma is smaller than -1. So somehow these two are opposite, and in this talk we call this case case A and the second case case B. Now algebraicity result is like this. So let us consider an algebraic Hecke character, not necessarily finite, and whose type Mn is critical. Then in the case A, we have algebraicity like this. So special value at 0 of this Hecke L-function divided by, I don't define Cm period, but this is somehow defined using Cm abelian variety related to this Cm field. So it is some kind of determinant of the period matrix of abelian variety related to this Cm field, and after Dulin basis and Betz basis is normalized suitably.
If you change Cm type sigma k, choose another set, then the range of this critical value changes.
Change Cm type?
You choose another sigma k.
I haven't considered, sorry. So maybe
Yeah, that changes.
that changes. Okay.
So Cm case, Katz p-adic function dependent on the sigma k. So there's a lot actually, 2 to the degree p-adic function exists.
Okay, thank you. Okay, thank you. And so algebraicity is defined like this. So this is element like this. So we multiply by this multi-index object and divide by this period. And in case B, in case A, algebraicity like this. And in case B, so this is opposite. And since all index has to be non-negative. So anyway, in this case, we have algebraicity like this. This is algebraicity for Cm Hecke character. Okay. So then we go on to the case of Artin L-function. So suppose first that K is totally real, and we consider continuous representation, so Artin representation of GK. And now we assume that the field corresponding to the kernel of law is totally real. In this case, we have the following algebraicity for critical special values. So if for positive integers, we have algebraicity for satisfying n satisfying this parity, and then the algebraicity is that special value at n divided by powers of pi to this power is algebraic. And like in the case of Hecke characters, in total real case, for negative integers, we have no period. So algebraicity is just special values itself is algebraic. So maybe you have comment.
I'm a little, I mean, no weight one form, say over Q, has critical point. That associated Artin L-function. So that's a little strange.
But indeed, we assume that K law is totally real. So
K law is totally real.
Yes, weight one case is odd. Weight one.
I see.
Yeah. Yeah.
That's the point. Okay.
Yeah. So we don't consider the odd modular Gara representation for weight one form. That case, as Hida said, we have no critical values. Yeah. So in this case talk, we don't consider this kind of Artin representation. This is another story. So we are excluding. Yeah. Grieb and Van Batsal was working with another idea, but this is totally disjoint from the subject of this talk. Okay. Okay. So now we go on to the p-adic world. So first, we consider any algebraic number field K, and with this notation K tilde, we mean the composite of all GP extensions of K. And this time by gamma K, this gamma K is not cyclotomic Gara group, but this Gara group or this total GPD extension. This is our notation for gamma K. And Leopoldt conjecture says that gamma K should be isomorphic to the power of 1 plus GP to this power, R2K plus 1. The R2K is the number of non-real embedding of K to C, modulo complex conjugate. So especially Leopoldt conjecture says that if K is totally real, K tilde is equal to the cyclotomic GP extension. And this conjecture is known for abelian extension of Q or imaginary quadratic extension, imaginary quadratic field.
What do you mean by 1 plus CP?
Oh, 1 plus PGP. Sorry. I forget. Yeah, sorry. Yeah, this here we should have 1 plus PGP. So P0 subgroup of GP close.
Yeah, exactly.
Yeah, sorry. Yeah, thank you. Okay, so by cyclotomic, we mean usual p-adic cyclotomic character, and with the notation kappa, we kill the torsion part of this character. So we multiply chi-cyclotomic character by inverse of the Teichmüller character. This goes to 1 plus PGP. And this is what we use. Okay. Then also another notation is if phi Gara character of finite order of this gamma k, then again by Brauer theory, phi is regarded, phi is correspond to algebraic character of finite order. So we sometimes denote by the same symbol by Hecke character corresponding to phi. Okay, so in case total real, we know the one variable p-adic function, p-adic Hecke function constructed by these people, so Deligne-Ribet and Cassou-Nogues and Barsky by different method. So we consider psi an algebraic character of finite order over this our total real number field K, and assume that K(C) is total real. And for simplicity, we assume that C is non-trivial. Otherwise, we have 4. Then we have an element in this Iwasawa algebra, and this p-adic function satisfies the following interpol property. So if you consider power of J or any non-positive integer, and we also move phi in the set of finite Hecke character, then we have this kind of interpolation property. So this is just special value for this Hecke L function twisted by phi inverse omega minus J. And we consider the special value at J. And we just multiply by this Euler-like character. And in fact, p-adic function is characterized by this interpolation property because these points are Zariski dense. Okay, we quickly go to CM case. So in the CM case, we have some kind of standard p-adic L function, but this is no more cyclotomic and not one variable. And in this case, if K is degree 2D, our p-adic L function is D plus 1 variable and lives in the weight space of this gamma K. And we also have some subtle change of the situation. We consider unramified.
So you assume Leopoldt.
I'm assuming Leopoldt. Yes.
Ah.
Is it okay? So we consider psi algebraic character of finite order on our CM field K, and psi is utmost terminally ramified at the primes over P. And did I explain CM? P-ordinary CM type. Maybe I will explain later. Maybe I missed some notation. Okay, maybe I will explain later. So anyway, in this case, to consider p-adic L-function in this setting, we have to assume some kind of ordinary situation. So we need to choose, so not any CM type is okay. So we have to choose CM times sigma k, which is p ordinary. And sometimes p ordinary CM times doesn't exist depending on p. So p ordinary CM type exists if and only if all primes over p of k plus split at k. Then we have CM or p ordinary CM type, and we choose one of them. Then there exists p-adic L-function depending on this sigma k, and the interpolation property is like this. Well, okay. So if we move critical algebraic character of type Mn, which satisfies critical conditions like type A and type B, which I talked earlier, then we have following interpolation property. So we can specialize our element by Gara character of eta, so which is p-adic number, and we divide this by p-adic period. And so this should be algebraic. Then this must be equal first to the this L value divided by CM period and multiply some kind of p-adic Euler factor. But then the interpolation property is much more complicated than totally real case. We have a lot of different factors. So like this factor, and this is local root number at p, and this is somehow multi-index gamma function, and powers pi, and discriminant of k plus. And this delta, maybe I don't explain, but this is something which appears for polarization of CM abelian variety corresponding to this situation. Maybe I will explain again in the next page. So p-adic period is p-adic analog of CM period. It lives in this group, and p-adic CM period is what I talked earlier. And delta, as I said, is polarized divisor of CM abelian variety. So this is a number of an element of this number field K, and this gamma factor multiplied multi-index gamma function is like this. So because this max is positive, so it is somehow product of factorial, so integer, and WP eta, as I said, it is local root number, and R eta. So this is just, there are some integers corresponding to this. This is a kind of normalization. And so, which one? Okay, oh, sorry. This one. Sorry. I forgot O and Rami height. So we tensor product over Z, and so this is more or less GP unramified hat. So and extended to O. So somehow this is bit ring of FP bar. Yes, yes, yes. Yeah, I forgot. Yeah, this is typo. So this should be OUR hat. Thank you. Okay. So I don't talk about the construction. But anyway, so basically, okay, maybe this one is constructed usually using the compactification of Hilbert modular variety, but they have another method. And very roughly speaking, we consider family of Eisenstein series, and we evaluate this p-adic family at CM point. That gives p-adic L-function. So that's what Katz does, and Hida-Tilouine has some kind of refinement of Katz construction. But basically, the construction is always the same. Consider p-adic family of Eisenstein series and evaluate somehow at CM points. Okay, so now we go to Artin L-function. So we consider CM number field of degree 2D and assume that P is absolutely unramified over P. And we consider Artin representation of GK. And in our work, we assume that this Artin representation is unramified at all primes lying over P. And we also assume that the field K rho corresponding to the kernel is also a CM field. And basic assumption, our setting, is like in the previous case for p-adic Hecke function. So CM times sigma k we consider is always assumed to be p ordinary. So again, so as I said, this only exists if we satisfy these conditions. And we also assume Iwasawa main conjecture of d k prime plus one variable, any intermediate field of this finite field extension and any algebraic character of finite order on this k prime. So I haven't checked completely, but basically there are some results, of course, already by this Hida-Tilouine's work, they prove under certain assumption half of the divisibility. And then there are also work of Min-Lun-Hsieh. And so with these works, possibly there are some other works. Maybe there are a lot of cases which are already proved. But anyway, so what is known exactly is complicated. So I just assume here the validity of Iwasawa main conjecture.
But the main conjecture depends on the choice of sigma k.
Right? Yes. Okay. So yes. Well, so the first theorem is like this. So if we consider low Artin representation with the previous assumption, we have p-adic Artin L-function, which has interpolation property like this. So this is d plus one variable. And if we divide by, so if we specialize at every Hecke character, which are critical, and divide by period, then it is related to special values with this interpolation property. So it's similar to p-adic Hecke function, but we consider Euler factor corresponding law, and somewhere we multiply the dimension of law. So this is what we get. And to state the second theorem, we recall Selma group. So maybe already appeared in several talks. But Selma group for Artin representation law over K tilde is defined to be the kernel like this. So we consider a Gala cohomology with A law. A law is, so we just choose lattice of Artin representation space of a law, and this is discrete representation corresponding to this lattice. And we consider discrete Gala cohomology like this, and we consider this kind of local condition corresponding to our CM type. And this is our Selma group in this case. Okay, so one important comment is that so we choose lattice here, but in general, depending on lattice T, Pontiac or Selma group might have different mu invariant, but in this setting, we calculate by Euler-Poincare characteristic formula, and there is some kind of annihilation. And if we calculate, in this case, mu invariant of Pontiac integral of Selma group doesn't depend on the choice of T.
I think you need to suppose the law reduction model residual representations reduced for something like that you need, no?
If we assume, you mean irreducibility of residual representation, then lattice is unique, but we don't assume. So it depends on the lattice T, but in this case, mu invariant doesn't change. Okay, so the next second theorem is main conjecture for law. Of course, we are putting strong assumption on the validity of main conjecture for rank 1 Hecke character, so of Hida-Tilouine type, but assuming that this Iwasawa main conjecture, D+1 Iwasawa main conjecture for degree 1 characters are true, we prove that our Artin p-adic L-function satisfies this kind of equality of Iwasawa conjecture. So that's our second theorem. And then in the rest of time, I explain a bit the ideas of the proof. So as I said, we use Brauer induction of law for law, and we prove first this kind of proposition A. So this is a weaker version of Theorem A. So we have p-adic L-function with the same interpolation property as Theorem A, but we only know that p-adic L-function is in the fraction field of this thing. So this is proposition A. So first we prove this proposition A by Brauer induction theorem. So like in the case of classical Artin L-function, we consider this kind of expression by Brauer induction theorem using degree 1 Gala representation. And then for each of them, there are Katz Hida-Tilouine type of p-adic L-function. So we consider this. This is what we explained earlier in previous pages. So this L prime is defined just, okay. So then this, for each phi I, this Hecke character is defined over different intermediate ki. So gamma ki, the number of variables of gamma ki is different depending on I. So for each I, we have surjection from this bigger Iwasawa algebra to d plus 1 variable Iwasawa algebra. This is what this is pi. So p-adic L function for each I lives here, but we want to define something here. So we consider the image of this element to the power ai and just multiply. This is L prime. So what we have to do is that this L function satisfies the interpolation property what we want. So by definition, so this is defined to be this kind of as a product of the image of this. So if we specialize this, we just have product from I to 1 to R of the interpolation, what we obtain with interpolation property for each p-adic L function this. So we just have this kind of product, and we somehow want to prove that this is related to our interpolation property.
Is this Ki a CM field?
Sorry?
Ki is a CM field?
So we are assuming that K-rho is CM field. So it's CM. So
okay,
this,
okay.
Yeah. So that's our assumption. Important assumption is K-rho is CM field. So all intermediate field, Ki, are also CM field. Okay. Yes, yes. Somehow we just consider diagonally, this Ki is over K. So Galois character, we can somehow consider multiplicate diagonally, and we can specialize by eta Galois. So what we have to do is that product is somehow equal to interpolation property. So this product, we have to relate this to this product. So we call this process the matching. And there are a lot of factors like Euler factor, gamma factor, and complex period and p-adic period. So if you try to do this matching, some of them are quite easy, just straightforward. For example, matching of special values L function is just straightforward. So we consider this. So L function of this, so direct sum, as also explained in yesterday's talk, is just product, and it is straightforward to prove this product is equal to twist of Artin representation. That's, for example, straightforward. And also, Euler product, matching of Euler product also not difficult, almost straightforward. On the other hand, matching of epsilon factors are a little bit difficult, and we have to justify that these are equal to this one. And to do this, we need some kind of generalization of Davenport-Hasse relation. And we have to do that carefully. And also, matching of period is also a bit difficult. So it is not a problem of calculation, but we have to justify that this matching, this product is finally related to the product of period, what we want. And so some of matching is easy and some of matching difficult, like p-adic period, complex period, polarized divisor. Justification calculations are a bit difficult, but we do all the matching of the factor, and then we obtain, we prove that this L function is interpolation, satisfies the interpolation property we want. Okay, I have to go more quickly. Then on algebraic side, what we have to do is specialization of characteristic ideal and relate this, relate this Selma group, which appear in main conjecture, to this characteristic, specialization of these characteristics and product of this. And this we call, we have to prove this, and this we call descent argument. So we developed already this kind of descent argument in this CM setting in previous paper. So using our technique, we consider this, we prove this descent. So first idea is that Selma group also is decomposed by this Brauer induction. So we prove descent argument for each of them. And so each of them are finitely generated torsion.
So this is in the Grothendieck group, right? AI can be negative.
AI can be negative.
Yeah.
Yes,
So
yeah. Yes. And so what we want to prove is this kind of equality. So this characteristic ideal is equal to specialization of characteristic ideal over Ki. So one important idea is to use strict Selma group, and strict Selma group is similar to the definition of Selma group, but in the Selma definition of the Selma group, we use inertia, and we replace inertia by decomposition group as a prime over P. And this is our strict Selma group. And this is by definition a subgroup of the original Selma group. And first, we prove that in our situation, strict Selma group is a pseudo isomorphic. Contrary ideal of pseudo Selma, strict Selma group is isomorphic to contrary ideal of usual Selma group. And descent argument is easier if we work with strict Selma group. So we will prove descent of the descent property was strict Selma group in place of Selma group. And then what is good with strict Selma group is it's easier to prove control theorem like this with Strict-Selma group. This is one good point with Strict-Selma group. And also, control theorem is related to descent, the proof of descent, validity of descent property, but the validity of control theorem is not enough for the proof of descent property. So sometimes there can be pseudo submodule, and if we specialize pseudo submodule from D plus one variable to D variable, it can have characteristic ideal. So we don't want to do that. So we have to prove that this kind of thing doesn't happen. So with strict Selma group, it's easier to prove the non-existence of pseudo Selma group. So that's what we do. And in fact, with strict Selma group, we prove descent property of strict Selma group. I finished in two or three minutes, sorry. And we prove proportion B. Then just combine. So
we are using this.
Okay. Okay. Sorry, I finish quickly. So proportion A and proportion B then imply. So somehow we prove it simultaneously. So if we prove main conjecture, this side we know that this is ideal integral. So we prove that this is integral. So from proportion A and proportion B, we prove theorem A and theorem B. Maybe I don't have, this is final page, but maybe I stop here. Or...
Yeah, thank you very much for your talk. Are there comments or questions in the audience? I can't see anything in the chat so far.
When you stated the interpolation properties, when we had theorem 3, we had an L function for a character involving omega to the minus j, and then evaluated at j. So j appeared twice. But now in these other theorems, you have the L function of a tensor product of two characters evaluated at 0. So how do those viewpoints interact with each other?
You mean j is moving, like?
Yeah.
Okay. So L function, value of L function at j is the same as this Galois representation twist by j's power of cyclotomic character. Then number variable is translated to j. So in CM setting, we don't consider cyclotomic character. So we always move Hecke character. But if we want, we can do it similarly in total real case. In place of moving j, we can consider changing the algebraic Hecke character twist by a norm character to the power j. Then you always consider special value at 0.
Then you can move it to 0, I see.
Yeah.
And that's different than the omega to the minus j. It's a different character that you're twisting by.
Oh, omega to, that's more subtle, but anyway, that small things, yeah. But yeah.
Thank you.
Can you pass the microphone?
So if you assume the main conjecture for Hecke characters, you get the main conjecture for these p-adic Artin L functions.
Yeah, that's what we do. Yeah.
So then the claim is that the p-adic Artin L functions are integral and have no poles.
Sorry?
So my question is so because you have the main conjecture for the p-adic Artin L functions, which is now the ideal generated by that is some ideal generated by the characteristic ideal of the Selma group. So the p-adic Artin L functions have no poles.
No pole. That's
So-
what we do.
So then can you say something about the complex L functions?
No. Sorry. Nothing on.
Yeah, so that's my question. So it seems like you've gotten the fact that the p-adic Artin L functions have no poles, and why can we not is there some information about the complex L functions that we can deduce from that?
I think maybe we get no information on classical Hecke function. Yeah. So we obtain nothing for original L function.
Any further question, comment? So we resume at 5:30 and thanks the speaker again.